All right, welcome back. Today we are going to be discussing chapter 4, basic probability. This chapter is very important. You have to make sure you get a good grasp on basic probability. This is going to be the foundation for statistics and for everything we do. Getting a good understanding on this chapter will explain to you why you shouldn't go to the casinos and take all your paycheck uh, and gamble it at the casino, and you're going to find out your probability of becoming a millionaire or winning the jackpot are very small. So uh, this chapter again very important for everything we're doing in the statistics and for things you do in real life as well. Okay, so the objectives for this chapter is to understand basic probability concepts, to understand conditional probability. We're going to talk a little bit of Bayes' theorem, and we're going to finish applying counting rules. So counting rules are also going to be very important for everything we do in the statistics, and very important that you grasp those concepts. If you are struggling with them, something you don't understand, please reach out. Let me know so I can provide you with resources, whatever you need to. But again, this is the backbone of statistics. Okay, so what is probability? When we're talking about probability, what are we talking about? Basically, it's the numerical value that expresses the ratio. So probability is the ratio between all possible values and the values that will occur. So you're going to find out that probability is going to be the foundation for distributions, mathematical expectations, binomial and Poisson distributions, which we will discuss later in statistics. So, for example, you want to know the probability can be used on intent to purchase survey responses and associated with follow-up responses to answer many purchase behavior questions. So the book talks about that example where they send this survey to 1,000 households, and so many of them say they are likely to they are thinking about purchasing, and then how many they said they're not thinking about purchasing, and then how many purchased and how many didn't purchase. So we'll talk a little bit about that later. Let's start by talking about the sample space. This is something that we'll discuss, and that's something you need to understand when we talk about the sample space. So what is that? Basically, it's all possible outcomes of a variable. So if you have a coin and your sample space is going to be 2, because the coin could be either heads or it could be tails. So your sample space 2. If you have a die, then your sample space is going to be 6, because you have 6 possible outcomes once you roll the die. If you have a card and you need to pick a random card, your space is going to be all the 52 cards, assuming you have a full deck, that are going to be on the bridge deck. So each possible outcome of a variable is an event. When we're talking about an event, we talk about each possible outcome that is going to result. So a simple event will be an event that is described by a single characteristic. So only one characteristic of that event. An example, I say pick up a day in January from all the days in 2022. So when you pick up that day, that is a simple event because it's just one day, it's in January, and that is a simple event. A joint event is an event described by 2 or more characteristics. So if I tell you pick up any Wednesday from January in 2022, now you have less options, right? Because there are only so many Wednesdays that are part of January for 2022. So you have you have 2 characteristics. The first one, it has to be a Wednesday. The second one, it has to be during the month of January. So again, simple event is just one characteristic, joint event, 2 or more characteristics. And then we have complement of an event. So you have your event A, and then you have your complements. So all events that are not part of A are going to be the complement. So for the first example, your complements are going to be any day that is not in the month of January. So any day in February, March, April, and so on and so forth are going to be the complement for event A, which is picking a day in January from 2022. Uh, Probability, again, is the numerical value representing the chance, likelihood, or possibility that a certain event will occur. And is always going to be between 0 and 1. So if it's 0, that means it's an impossible event. So there is no possibility that such thing will happen. So for example, if I say, the probability that it's going to snow in the city of Panama, in Panama is 0, is because, ever since we started tracking the weather, it has never snowed in the city of Panama. So in that case, I can tell you that the probability that tomorrow is going to snow in the city of Panama is 0, because that is impossible. It's not going to snow there. The weather and the conditions do not allow for snow there. Now, if an event will occur for sure, then you can say the probability of that event occurring is 1. So if I tell you the sun is going to rise tomorrow, I know we know better that the sun doesn't rise, the air that runs, that gravitates around the sun, we know that, of course. But, just for talking characteristic, we say, the sun rises. Um, and I can tell you the probability that the sun is going to rise tomorrow is 1, because for the last 5.3 billion years, the sun has been rising every day. So that is a certain event. Now we can have events that are mutually exclusive. And what I mean is that they cannot occur at the same time. So if you are flipping your coin, right, it can either be heads or tail, but it cannot be both. Another example is choosing a day from January from 2022. And so uh, event one will be a day in January, event two will be a day in February. Those two are mutually exclusive because a day cannot be both in January or February. It can only be on 1 month. Now we have events that can also be collectively exhaustive. What does that mean? That means one of the events must occur. So when I say, okay, flip a coin, it's either going to be heads or tails. So one of those are the options, okay? And and so one of those will have to choose. So if I say also choose a day from 2022, it has to be a weekday, B has to be a weekend, C it has to be in January, D has to be in spring. So on this case, right, A and B are mutually exclusive because it can only be a weekday or a weekend. Okay. Now C and D are not mutually exclusive because it could happen in January or it could happen that they could be in spring. But those are not exhaustive because um, it could also happen during the fall or during the winter. So those are not collectively exhaustive. So events A, B, C, and D are collectively exhaustive. All four of them are, but not mutually exclusive because a weekday can be in January or in springs. Now, events A and B are collectively exhaustive and also mutually exclusive because if one happens, the other one is not going to happen. So there are three different approaches that you can do to when it comes to assessing the probability of an event. The first one is what we call a priori. So that is based on prior knowledge that you have. So the probability of something occurring, here you're assuming that all outcomes are equally likely, right? So all the outcomes are equally likely. So the probability of occurrence for a priority means that the number of ways in which the event occurs divided by the total number of possible outcomes. We can also have the empirical probability, and that is based on observed data. So you have the probability of occurrence is going to be the number of ways in which the event occurs divided by the total number of possible outcomes. And then you have the subject probability, and that is based on a combination of individuals' past experience, personal opinion, and analysis of a particular situation. So let's discuss a priority probability. So again, this is based on prior knowledge, right? When randomly selecting a day from the year 2022, what is the probability that day is in January? Based on prior knowledge, we already have to know this, and we do. we already know the numbers of days that we have in January. So every January, uh, there are 31 days. Also, on prior knowledge, we know that the year 2022 has 365 days. So the probability of picking a random day for the month of January is 31 divided by 365. Here is empirical probability. So this one is, in this case, we're trying to find the probability of selecting a male taking a statistics class from the population described on the following table. So in this case, we found 439 students, and so we asking what their gender was, and then we asking if they were taking a statistic class. So out of the 439, 229 say they were males, 210 say they were females, and out of those, 160 said that they were taking a statistics class. So based on this, we take the number of males that are taking statistics, that's 84, and then we take the number of total students that we asked, and that's 439. So the probability of selecting a male students out of those 439 students that we asked is 84 divided by 439, or 19.1%. Now, subjective probability is a little bit different because that is based on a person's personal opinion. So if you ask some experts, who do you think is going to win the Super Bowl? So some experts might say, oh, it's going to be this person. Some other people might say it's going to be the other person. So that is going to change based on who is uh, giving their reasoning for a particular team winning the Super Bowl. So in this case, you can ask the question, what is the probability of new ad campaign being successful? And then somebody might say, a media development team might say, oh, 60% probability that that will happen. While the chief media officer, he say, I have more experience. I've seen this before. I gave 40% of success to the same campaign. So different people might give them different possibilities. Again, some people say, oh, this team A has 80% probability of winning the Super Bowl. Some other people say, oh no, this team has 75%. The assignment of subjective probability is based on a person's experience, opinions, and analysis of a particular situation. So, they're going to say, oh, you know what, such a player is injured, and oh, you know what, the team struggles when it comes to rush offense, things like that. They're going to give in their different opinions. So subjective probability is useful in situations when an empirical or priori probability cannot be computed. In the case of the Super Bowl, I know they have computers that give you statistics and cannot tell you, or based on on certain situation, which team is more likely to win. But you're also going to have the subjective probability that can be useful when empirical or priori probability cannot be computed. Remember chapter 2, we talk about summarizing samples and other data. On this one, you will summarize sample spaces. And on this case, you will have people that plan to purchase TV, yes or no. You have your totals. And on the other side, you will have the actual purchase TV. You will have yes or no and the totals as well. Here is the sample space. Remember, that is the total possible outcomes. That will be 1,000 because that is the number of people they interview. You can also do Venn diagrams, and Venn diagrams like this one here, you can see the circle A is the ones that plan to purchase, right? And then the one, you also have the one that did not plan to purchase. You have B who actually purchased, and the ones that did not purchase. So A united with B, all right, that will be the entire space right there. That would be 350. That's the and where A and B intercept, that is the 200, and that is the people that plan to purchase a TV and actually purchase the TV. So simple probability refers to the probability of a simple event, right? We have P, which is the plan to purchase, and we have the P, that probability that actually purchase. So the probability of A, which is the numbers of outcomes satisfying A, divided by the total number of outcomes. So in this case, you want to find out how many people actually purchase a TV, right? So you have the people that plan to purchase, the people that actually purchase. When you add the people that say they were not planning to purchase, but they end up purchasing a TV, you'd get a 300. So that's the number of outcomes satisfying A. And then the total number of outcomes, which is the 1,000, that will be your denominator. So 300 divided by 1,000, or 30%. Joint probability, okay, refers to the probability of an occurrence or two of more events. So basically, you have two events joined together. So in this case, you want to find out how many people say, you know what, I am planning of purchasing a TV in the next 6 months, and how many of them actually purchase a TV on the next 6 months, right? And then you have the probability of those who did not plan to purchase a TV, but also purchase a TV. So what you're doing is you are joining two different data here. So you have probability of A, which is plan to purchase and actually purchase, and B, those are that did not plan to purchase but actually purchase a TV. So on your numerator, you are going to have the numbers of outcomes satisfying A and B, and at the bottom you're going to have the total numbers of outcomes. So when you look at the data here, right, you had the people that plan to purchase a TV was 200, and you had the people that did not plan to purchase a TV, but they end up purchasing a TV of 50. So what you do is you add those two. So how you compute a marginal probability via joint probabilities? So what you're going to have to do is you're going to compute a marginal or simple probability, right? So probability of A, which is going to equals the probability of A and B1, right? Plus the probability of A and B2, plus L, plus the probability of A and B with the numbers of observations that you're going to do. B1, B2, and BK are mutually exclusive and collectively exhaustive events. So to put this into simple words, right? So you have P, people that plan to purchase a TV, right, is going to equal the probability yes and yes, so that they actually they plan to purchase the TV and they actually purchase the TV, right? Plus the probability of those who purchased the TV but did not plan on purchasing the TV. And that's how you get the 200 plus the 50. So going back in here, here is the one that plan to purchase and purchase. Right over here, you get this 200 divided by 1,000, and then here you get the 50 divided by 1,000. Once again, so here is yes and yes, yes and yes, which is the 200, and then yes that they plan that they actually purchased the TV, but they were not planning, so that is the 50, and that's how you get your 250. So marginal or joint probabilities in a contingency table. So you can put that on the table. Again, here you have your A1, B1, B2. Here are your totals. On this here you have event A2. So the probabilities, so again, you have joint probabilities here, right? The probability of A1 and B1. And then you have the probability of A1 and B2. So here is your A1, here is your B1, here is your A1, here is your B2, and here is going to be your total probability of A1. Just finally here, remember marginal probability of an event consists of a set of joint probabilities. So don't forget that, very important. So far, this is what we talked about it. Probability is the numerical measure of the likelihood that an event will occur, right? So something will happen for sure, you give them a 1. Something is impossible to happen, you give them a 0. In a 0.5 will mean it's equal likely to happen as to not to happen. So when you say I'm gonna flip a coin, the probability is 0.5 because it could be heads or tails. So the probability of any event must be between 0 and 1 inclusively. So here you have 0 has to be less or equal to the probability of A, which it has to be equal or less to 1 for any event A. And then the sum of probabilities for all mutually exclusive and collectively exhaustive events is 1. So the probability of A plus the probability of B plus the probability of C and so on and so forth, it has to equal 1. If A and B and C are mutually exclusive and collectively exhaustive. So let's say the probability of picking a day in January from 2022 is going to be, to all those probabilities, you add them and that should equal to 1. Here is the general addition rule. So the probability of A and B, or A or B, so remember this is not N, but A or B, right, is going to equal the probability of A plus the probability of B minus the probability A and B occurring together. So you have to subtract the probability of A and B happening together, if not you are double counting. On this case, remember A and B has to be mutually exclusive, like on the case of the coin, right? Is the heads and tails are mutually exclusive, so A and B has to be mutually exclusive, right? So you have the probability of A and B equals 0, and the rule can be simplified by saying the probability of A or B is going to be equals to the probability of A plus the probability of B for mutually exclusive events as A and B. So in the case of coin, which can be either heads or tails, so the probability of getting heads or tails equals to the probability of heads plus the probability of tails, which is 50-50. In this case, obviously 50-50, 0.5 plus 0.5 equals to 1. So going back to the example that we're talking about, purchasing a TV. So the probability that plan or purchase, right? In this case, we're saying plan or purchase. So is going to equals to the probability of that you plan to purchase the TV. So that's 250 divided by 1,000 plus the probability of those who actually purchase the TV minus the probability of those who plan and actually purchase. So very important again here, because these are not mutually exclusive, because somebody can plan and purchase the TV, so that you subtract that. So let's break this down. Here you have the probability that plan to purchase a TV, right? So here plan to purchase a TV, 250. That's what you get, 250 here. Again, you are dividing always by your total sample here, which is 1,000, right? Then you have the probability of those who purchase the TV, which is 300, right? So you have 300 divided by 1,000, and then you're going to subtract those who the probability of those who plan and purchase the TV. So you want to see who plan to purchase the TV, and then who actually purchased the TV, and that was 350. We already have that. That was 200. I'm sorry. This is right over here, right? Plan and purchase. So this 200 here, that's the people who actually plan to purchase. Yes, actually purchase. Yes, so that's the 200. So you have to subtract the 200. If you don't, then you are counting them twice. Once you subtract the 200, you get the 350, or 35% is the possibility of people who plan or purchase, picking somebody who actually plan or purchase the TV. Computing conditional probabilities. A conditional probability is the probability of one event given that another event has occurred. So you can say, what is the probability of B given that A has already occurred? And that is going to equals to the probability of A and B divided by the probability of B. So the conditional probability of A given that B has occurred. On the other one, you have the conditional probability of B given that A has occurred. So you have the formula there is very similar to just moving the letters. And so remember, probability of A and B is the joint probability of A and B, and probability of A is the marginal or simple probability of A, and the probability of B of the marginal or simple probability of B. Uh, let's take a look at an example to put this a little bit into perspective. So what is the probability that somebody purchases a TV after they plan on purchasing a TV? So the probability is going to equal the probability of purchase and plan divided by the probability of plan. So the probability somebody is going to purchase and plan, remember? So yes and yes, right? That is this 200 here divided by the total sample, 1,000. And then you're going to divide that by the probability of those who plan to purchase a TV. So here it is, the probability of those who plan to purchase a TV is 250, right? These people say yes, and these people say yes, that's 250. So 200 divided by 1,000, and then you have 250 divided by 1,000. When you simplify those, you have 200 divided by 250. Here is a decision tree, and this is an alternative to contingency table. If you want to use the contingency table like the one you had before, you can also use this. Here is all your 1,000 households that you interview, and then you have the ones that plan, right? 250 divided by 1,000. Those who did not plan to buy a TV, you have 750 by 1,000, and then here you have your conditional probabilities. So purchase, that's the probability of A and B. Did not purchase, right? That's the probability of A and the B who did not purchase. And then you have your the ones that did not plan to purchase but end up purchasing, and the ones that did not plan to purchase and end up not purchasing. So you can use this decision tree to calculate your probabilities too. Uh, Independent events. What are independent events? What are we talking about when we say independent events? Basically, those are two events that are independent if and only if the probability of B given A is going to equal the probability of A. So basically what we're saying here is events A and B are independent when the probability of one event is not affected by the fact that the other event has occurred. So are the events plans or purchase independent? So are the events plan and purchase, are they independent or are they joined together? And so does the probability of purchase uh, base, if they already planned, is going to equal the probability of purchase? So let's take a look at here. So the probability of purchase, and if they already planned, is 200 divided by 250, and that equals 0.8. And we see that the probability of purchase is 700 divided by 1,000, or 0.7. And because they're not equal, we can say these two events are independent. So here it is, right? Two events are independent if the probability of A, given that B has occurred, equals to the probability of A. On this case, we saw that was not the case. So we can say these two events are dependent, right? Because the probabilities are not equal. Multiplications rule for two events. We have the general multiplication rule, which is probability of A, B is going to equals to the probability of A and B divided by the probability of B. And then once you solve for P, right, A and B, basically you can say the probability of A and B is going to equals to the probability of AB times the probability of B. On this case, you can say that A and B are independent, and then you can say the probability of A and B is going to equal the probability of A, and the multiplication rule can be simplified to you saying to the probability of A and B equals to the probability of A times the probability of B. What about the marginal probability using the general multiplication rule? So the marginal probability for event 8 equals the probability of 8 is going to equal the probability of A B1 probability of times the probability of B1 plus the probability of A B2 times the probability of B2 plus L plus P, probability of A and BK, and so on and so forth. So in this case, remember, all of these B's are mutually exclusive, and all of them, right, collectively exhaustive events. I know that's a lot of to take, so let's just put it a little bit into context, right? You have, in this case, A is the people that plan to purchase the TV. B1 will be those who actually purchase, and B2 will be the one that not purchase, right? So the probability of those who plan to purchase a TV is going to equals to the probability of those who purchase because they plan to purchase a TV times the probability of those who purchase the TV plus the probability of those who purchase the TV, who purchase the TV after they plan to purchase the TV times the probability of those who did not purchase the TV. So here is that multiplication, right? Basically, the probability of A is going to equals to the probability of A and B1 times the probability of B1. So A is the one who planned to purchase the TV and did not purchase. So you can see that one, that's the 200 here. And the you divide that by the 300. And then you multiply that times 300 divided by 1000, right? That's the one that that's the probability of B1, right? Probability of those who purchase. So here is actually purchase the TV 300 divided by the 1000. And then you are going to add the probability of those who purchased the TV but did not plan to purchase the TV, right? So that is this 50 here. Actually purchased a TV, but they did not purchase a TV, but they actually plan to purchase a TV. That's where the 50, and then you divide that by this 700 here. And then finally the probability of B2, which is the one that did not purchase the TV, and that is the 700 divided by the 1000. So after you do all of the multiplication, you get 0.25 or 25%. One thing you need to keep in mind is the issues of ethical. So ethical issues can arise when any statement related to probability are presented to the public. You see that a lot. People manipulate data. They do it on purpose in order to deceive and mislead and say, oh, you know, this is 75% of this is 60% of that. Also, unintended misinterpretations can occur when people who are not comfortable with numerical concepts and they just present that data there. Finally, advertising quoting probabilities can also be intentional misleading. So we can see that in advertisements, so you see that, oh, 9 out of 10 doctors recommend this toothpaste, right? They don't tell you that those 9 doctors actually work for the manufacturer. So that could be an issue when it comes to probability. Okay, let's talk about the Bayes theorem. So this Bayes was a statistician that lived on the, I believe, the 1800s. And he came up with this theorem that is used to revise previously calculated probabilities based on new information. So you already have some information, and then he said, you know, you can calculate probabilities based on new information. So it was developed by Thomas Bayes in the 18th century, and it's an extension of conditional probability. So here is the Bayes theorem, right? You have the probability of BI given that A has occurred is going to equal to, you know, here's the formula. And on this case, B1 is the ith event of K mutually exclusive and collectively exhaustive events. And A is the new event that might impact P, B, and I. So basically, you have a new event that will have an impact on it. And that's when you will use the Bayes theorem. Here is an example when you will use Bayes theorem. Let's say you are a drilling company and you say, well, after doing some research, we calculate that it's going to be a 40% chance of getting oil out of this new well. And then you detail a test that has been scheduled for more information. So basically you do some more research and you say, well, historically 60% of successful wells have the tail test, and 20% of those unsuccessful wells have also had the tail test. So all of a sudden you got more information, right? So given that this well has been scheduled for a detailed test, what is the probability that the well will be successful? You're trying to figure out what are the chances that this well is going to be successful. So in this case, you're going to take S is going to be a successful, U is going to be unsuccessful. So you already have the data, right, saying that the probability of a successful well is 40% or 0.4. That means, the probability of being unsuccessful is 0.6 or 60% or 60%. So you need to define the detailed test event as D, right? So then detail is going to be D, and then you have the conditional probability. What will be the condition of having a successful well if we have a detailed test? And in this case, we have that is 60%, and the probability of having an unsuccessful well, given that we have a detailed test, is 0.2%. So we already have the data, right? So we need to find the probability of having a successful well, knowing that we have a detailed test. So this is where the Bayes theorem comes into place. And we already had the formula a couple of slides ago. And on this case, we just gotta subtract the input the data that we already have in here. So 60% times 40%, and you will divide that by 60% times 40% plus, right, the probability of being unsuccessful, which is 0.20 or 20% times 60%. And once you simplify that, you get 0.667 or 66.70%. After you revise this, you came to the conclusion that this well has been scheduled for a detailed test, and there is a 66.7% of that wells being successful. So you're more likely to invest the money that you need to implement the well. Here it is, given the detailed test, the revised probability of a successful well has risen from 40%, right? That's what we had at the beginning, to 66.7%. And we can see that data here, prior probability, the conditional probability, and then you have your joint probability of 0.24, and then the successful of 0.12, and then you have your revised probability. Okay, we're going to finalize this chapter talking about counting rules, and those are very useful, very important, so let's go over them. In many cases, right, you have a lot of data, you have a large number of possible outcomes, so trying to figure all this out can be very cumbersome, so you have to use the counting rules because they will make things more easy to compute. So the first rule says that number one determines the number of possible outcomes for a set of mutually exclusive and collectively exhaustive events. So for any k different mutually exclusive and collectively exhaustive events can occur on each in trials, the number of possible outcomes is equals to k to the n. So if you say, if you flip a coin twice, what are the chance of getting heads twice, right? And in this case, you will have to do the possibilities 2 to the, and because you're rolling it twice, so you go to the second power, so that will be 4. On the example here, if you roll a fair dice 3 times, and each time there are 6 possible outcomes, so 6 to the third power is 216 possible outcomes. All right, counting rule number 2. Basically, this is kind of like a general version of rule number 1, but it allows the number of possible events to be different on each trial. So what you're saying here is if there are any k events on the first trial, k2 events on the second trial, and k and kn events on the n trial, the number of possible outcomes is k1, times K2 times L times Kn. So if you say, you can go to the park, eat at a restaurant, and see a movie, right? So there are three parks that you can choose from where to go. There are four restaurants that where you can eat, and there are six movie choices that you can see. So how many different possible combinations could there be? On this case will be K1 is 3, K2 is 4, and the Kn in this case will be the six different choices. So you multiply all of those and you get 72 different possibilities. So based on those six movies, the four restaurants, and the three parks, you can arrange them in 72 different possible ways. Counting rule number 3 is the number of ways that n items can be arranged in order. So you have n is going to equals n times n minus 1 times L times 1. So imagine, for example, that you have 5 books to put on a bookshelf, right? And you, how many different ways you can set these books on the bookshelf? And so you have 5 books, and then you will multiply 5, and you are subtracting each time you're subtracting because the book once it goes in the shelf say that, right? So 5 times 4, because you subtract 5 minus 4 equals 1, and then you subtract that again, and then you get 3, and then you get 2, and then you multiply by 1, and that will equal 120 different possibilities. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 equals 120. On this one, you're computing the number of ways a set of times can be arranged in order. All right, counting rule number 4 is the permutation. Basically, this is number of ways of arranging X objects selected from N objects in order. So imagine that you have those 5 books, right? But you're only going to put 3 on a bookshelf. How many different ways can the books be ordered on the bookshelf? So out of those 5 books, on this case, you're only going to put 3 in there. So how many different ways you can do that? And on this case, right, you have n is the number of possibilities is 5, and then you divide by 5, which is the number of possibilities, minus the number of books that the number that you're going to use, which in this case is 3, and that'll give you 120 divided by 2. Right? Remember, we calculated, and the 120 is this here, right? 120 different possibilities. So you just have those 120 different possibilities, and then you divide that 5 by minus 3, that equals 2. So in this case, you only have 60 possible options because you're only putting 3 books on the bookshelf. You don't know which ones they are, right? That's why you have 60 possibilities. Okay, and the final counting rule, sometimes you might not be interested on the orders of the Econ, but only on the number of ways that X item can be selected. So each possible selection is called a combination. So in this case, combination would be the number of ways of selecting X objects from N objects, irrespectively on which order it is, right? So there is a formula there. And let's say you have those 5 books that we've been talking about, and you're only going to select 3, right, to read. So how many different combinations are there, ignoring the order which they are selected? So it doesn't matter which book you want to read first. How many different options do you have? Okay, we find 5 before, and that it was 120, and then we have 3 minus 5 divided by 3, 5 subtracted from 3, so that will equal 6 times 2, and that will be 12. So 120 divided by 12 is 10. So you have 10 different possibilities. You can choose 10 different ways on how to rearrange those books that you will want to read. All right, guys, I know this was a lot. Please go over the textbook. I hope this presentation helped you put this into perspective. If you still have questions, let me know. But it's very important that you understand, again, this is going to be the backbone of everything that we're going to be doing. So we covered using basic probability concepts. We used conditional probability, right? What is the chance of this happening if this has already happened? We talk about the Bayes theorem, so that's when you get new information, right? And you need to revise your probabilities. And finally, we did talk about those counting rules. Remember those 5 counting rules. Go over them, make sure you understand them, and you know how to use them. All right, reach out if you have any questions.